So I'm going to present a joint work with Vincent Laporte and David Pichardy, who was introduced in the previous talk. Like the previous talk, the context of this work is formal verification using a proof assistant of static analysis by abstract interpretation. Here in our static analyzer, the difference is that it operates over the C programming language. And in my talk, I will present an abstract memory functor that is one of the main components of this C abstract interpreter. So our work targets critical embedded software that you need to trust. For instance, when you need to convince an authority that your software is running as expected and as written in the specification, and such critical software is becoming more and more complex. So in industry, a common practice to get this confidence is to perform manual verification, so that you do manual code review. The problem with this technique is that it does not scale. So some people are also using automatic tools to find bugs. This tool may be successful. The problem is that they may miss some bugs. And so a more advanced way of using this tool is to use automatic tools that are also sound by constructions. And with such a tool, the tool may either fail or find all bugs in the software. A well-known tool performing this is Astray static analyzer developed by Patrick Couzeau and his team. This static analyzer scales. It is used in production in industry at Airbus, the airplane manufacturer, and it was used successfully to ensure that there was no false alarms in the most critical software on the Airbus A380. Astray is an impressive piece of software. It uses non-trivial standard abstract interpretation techniques. So this raises the question of how do you trust your verifier? And an answer to this problem is to use formally verified verifiers that are developed using a proof assistant, so you get in the end the verifier and its soundness proof that is machine checked. So how do you verify a verifier? A simple idea is to program and prove your verifier in the same language. We use the coq proof assistant. We can see coq as an animal with two faces. On the one hand, coq is a proof assistant, so you can interactively build proofs in constructive logic. And on the other hand, coq is also a functional programming language with a very rich type system. So the methodology we rely on to formally verify our static analyzer is the following. First, we program our static analyzer inside the functional language of coq. So we write the analyzer inside coq. Then we define a relation expressing the semantics of the language our analyzer operates over. And then we can write the correctness theorem. We can state the correctness of the analyzer with respect to this formal semantics. So we will write a theorem such as follows. For all program P, if the analyzer gives an answer that is success, no false alarm, then we are sure that the program will have a well-defined semantics, which means it will not go wrong according to the formal semantics we have previously defined. Then we conduct the proof, so we interactively prove these theorems, and in the end, we've got a certified implementation, since we can use the extraction facility of coq in order to generate automatically the OCaml implementation of the analyzer. This approach was already the one chosen for developing the Concert C compiler. This compiler comes with a proof that it does not introduce bugs. And this compiler scales. It was, for instance, used in industry at Airbus in order to compile fly-by-wire software, the flight control guidance unit of the Airbus A380. That is a big software that is the most critical software embedded in the airplane. This is a critical embedded software, so this is a C code that is mostly generated from skate block diagram plus a minimalistic operating system. So here we, following this concert experiment, we decided to develop a static analyzer operating over the C language called Verasco. This is a joint work with different French teams. And the idea here was to reuse some parts of concerts that we could use as a library for our static analyzer. So the language our analyzer operates over is a concert subset of the C language, which is almost C ISO 99. This analyzer is using non-trivial abstract domain, including relational domains. And its architecture is very modular and inspired from ASTRAE architectures. In the end, this static analyzer is able to prove the absence of undefined behavior, including a memory safety of C programs. And we have the following slogan. So in Concert, we were able to Concert can be seen as a small GCC compiler. We can estimate in terms of features that Concert is about 1/10 of GCC. So let's do the same with Verasco. That will be one day a small ASTRAE, but formally verified. So the main architecture of Verasco is the following. It was presented last year in a paper. So this analyzer operates over a low-level C that is defined, that is used in the Concert compiler. And this static analyzer has many layers, and each layer is parameterized by an underlying layer. So on the top, you have the abstract interpreters that is given a result. So either there is no alarm, or either it raises alarms. This abstract interpreter is following the control flow of the program, so it uses fixed point iteration using widening and narrowing techniques. Then this abstract interpreter is parameterized by a state abstraction, a state abstract domain. This state abstraction consists in defining an abstract memory and a value domain. And this state abstraction is itself parameterized by numerical abstractions. So in Verasco, there are different numerical abstractions that can be combined together. And in the POPL papers, we explain how this different numerical domain can communicate. And we also explain how the abstract interpreter works. In this paper, so the memory abstraction is very naive. And for instance, it doesn't finely track contents of array cells. It considers arrays as a single abstract cells. And so what we did in this paper is the following. So we define a new memory abstract domain that is parameterized. This is why we call it an abstract memory functor. This abstract memory functor handles the low levels feature of C that are pointer arithmetic, arrays with cells, and structs with fields. And it also handles unions, including performing typecast between values. This abstract memory functor is integrated into the Verasco analyzer, so we stick to the high-level interfaces that were previously defined in this analyzer. And so that we can exploit powerful relational numerical domains that were existing in Verasco, and we can also reason symbolically on memory addresses using these domains. Let's look at an example program to see the kind of property we would like to infer with our new abstract memory functor. So we have here a very basic linked list of integers. And what we would like to do is compute the sum of all the values stored in the list. So we can write a C program performing this task. It will compute that, for instance, the sum of this list is 28. And we are here in the context of critical embedded software. So let's suppose we are not allowed to use malloc in our C programs. So we have to implement this linked list in other ways. So we use here a C array to implement the list. And so it can be implemented as follows. And we want to have guarantees about this list. So we want our static analyzer to prove that, for instance, this sum variable we have written in our C program is an integer. We also want to prove that the P pointer we use to point to the current array cell stay within the array bound, as there is no check in C for that purpose. And we also want to prove that memory accesses are properly aligned. For instance, here, in the array, I showed the alignment constraints we can have on the program. So with the previous version of Verasco, we could not do this kind of verification, and now with a new memory abstract domain, we can check all these properties. So what is this abstract memory Functor? It has several components. The first one is a notion of abstract cell. A cell is a unit of storage. So it's an elementary unit to which is attached abstract information. We distinguish between two kinds of values. We have either registers storing values or a chunk that is a chunk of an in-memory variable. So we can access to a part of a variable. We just specify its size and its type. It's not necessarily the variable as it was stored in memory, for instance. It can be read differently. And we also have relational numerical domains. And here we use such domain to abstract the numerical content of abstract cells. So a pointer value in a concrete world in COMCERT is defined as a pair of a block and an offset. And here we abstract such a pointer. For instance, we may only have to care about its offset. So we use this numerical domain to abstract these things. And we also, we have pointer arithmetic in C. So to model pointer arithmetic in our abstract memory Functor, we design a points-to abstract domain that maps each abstract cell to the set of the variables it may point to. And here, this points-to domain needs to perform some conversions. So it receives C expression, including memory loads and pointers. And the role of this abstract memory Functor is to translate these expressions so that they can communicate with a lower level abstract domain where we don't have neither memory load nor pointers. So the abstract memory Functor needs to perform some conversions. There are two kinds of conversions. The first one is the elimination of loads. So for instance, here we have a C expression, V plus star P, where P is a pointer to an integer. So this is the initial C expression, and I need to convert this expression so that it can be used by the abstract numerical domain without load to the cell pointed by P, in this example, and without pointer, because in the numerical abstract domain, we do not have such features. So then this expression needs to be converted in order to be used by the numerical domains. And for this reason, the abstract memory functors embed two abstract domains, a numerical domain and a points-to domain. So we first, the abstract memory functor first need to eliminate loads so that we have load-free expression, and then it eliminates pointers so that in the end we have a numerical expression that can be used by all the numerical domains. In order to do these conversions, so the elimination phase need to access to some information that are stored in both domains. For instance, in order to eliminate load, A load is an access to a cell pointed by a pointer that is represented by a block and an offset. And in order to have a precise approximation of the block and the offsets, so the load elimination needs to have the information coming from the points to domain and the numerical domain. In the same way, the pointer elimination needs to have a type information that is stored in the points to domain. So in the paper, we give the signature of all these function for conversion of source expression, and we give more details about these conversions. So this is the interface of our abstract memory functor. It's written here in Coq. So this functor is parameterized by a type called T, that is a numeric abstraction. And we have several parts in this functor. First, we need to store abstract values that are ordered using a lattice, as in standard abstract interpretation. Then we have queries. For instance, here, the abstract domain may need to query, to send a query to the numerical domain in order to get an over approximation of a local variable in the program. And then we have abstract transformers. So this is a standard abstract interpretation, and here abstract transformer model the different instruction of the program. For instance, here we have two kinds of assignments, assign and store. The first one model assignment of local variable, and the second one model assignment to in-memory variables. So we distinguish between them in our static analyzer. So this is the interface of our functor, and we have implemented this interface in two ways, using two different numerical domains. So for the experiments that we have conducted and that are reported in the paper, we have done two implementations, one using a relational polyhedral domain, so a rather complex abstract domain, and another one using an interval domain with congruencies. So in the end, our abstract memory functor can be seen as a layered formalization. So I've mentioned points to a numerical domain. So this is the abstract domain. On the one hand, it tracks information about the contents of array cells. And in the concrete world, so the world of concert, we have a concrete memory where we have only block and addresses. And in order to prove the soundness of our analyzer, we had to design two more layers in this formalization. These layers are explained in detail in the paper, but the idea is that we needed what we call the functional memory, that is a total function from abstract cells to value, and we need to have the same for concrete memory. So in the end, we've got this, we have defined these three layers on the top of the concrete layer of concert that we reused. So we have written our analyzer in Coq. We have proved that it is correct. Then we could extract it and run it on real C programs. So we have done some experiments on different C programs. First on concert benchmarks. We have also run our analyzer on randomly generated programs by the Smith tool. It's a tool that generates very nasty programs that no human could write. And we have also tried our analyzer on bigger programs. On the one hand, cryptographic routines from the NACL library and from the Polar SSL library. We chose these libraries because they are implementing interesting instruction for memory, so they are using C arrays a lot. And we also tried our analyzer on an implementation of a SAT solver. So the idea here was to exercise many delicate aspects of C. Our memory functor can handle arrays, pointer arithmetic, and function pointers. So the first experiments were encouraging because our analyzer was able to analyze this program, but the performances of the analyzer were could be improved. So in the paper, we explain the 3 analysis extensions we have designed in order to improve the performances of the analyzer. For instance, the first one handles the unions and type pruning. So the idea is that you store, in your C program, you store a value with a given type, and you can read this value with a different type. And here, from the abstract interpretation, we are faced to the following program. So if we read a value with a different type, then we have a corresponding abstract cell, but this cell is not bounded to the previous one. So here we need to use a more advanced abstract interpretation techniques that is called realizations. I think I'm running out of time, so I will not say more about next 2 extension we have designed. So to conclude, we have in the end a formally verified static analyzer based on abstract interpretation, which establishes the absence of runtime error in non-trivial C programs. This static analyzer uses a fine-grained memory abstraction that is compatible with the Verasco relational domain. As a future work, we intend to improve the performance of our analyzer in order to precisely handle cells of array. We have designed a first extension that is called a summarized cell, where an abstract cell represents several concrete cells. And this abstraction is running, but it is only performing weak updates. So we intend to improve this extension and to perform, when we can, weak and strong updates. Another improvement is about dynamic memory, allocated memory. So we can handle it partially only during array initialization. So we intend also to improve this. And to a longer term, we were recently able to reuse our static analyzer in order to improve other analyses. So in this recent work, the idea here is that, okay, we have now a C abstract interpreter. It operates over C source language. It is quite precise. So let's reuse this static analyzer and let's transfer its results down to lower level languages of the compilation chain. So we were, for instance, able to transfer this result to the RTL intermediate language, where optimization are performed in concert, and we were able so to reuse some result of Verasco in order to improve a few compiler optimization. And we were also able to transfer the result down to pre-assembly level in order to perform a security analysis aiming at proving that a program is cryptographically constant time, which means that the secrets on a program do not depend on the memory, on the sequence of memory accesses, for instance. Okay, thank you.
I think we can take a couple of quick questions.
I'm Christine Riscala from UPenn, and I'm wondering, you said 2 things. You said that your static analyzer is like 10% of this known static analyzer, and I was wondering in what sense is it? Can it analyze less programs? Can it prove that less programs have are correct, or is it just slower at doing that?
It's 10% in terms of features. So Astray uses much more advanced abstract interpretation techniques that we do not use. And as a consequence, we we cannot, today we cannot analyze all the programs that S3 can handle. Yeah.
Phil Wadler, University of Edinburgh. So towards the end, you put up this list of impressive programs and said we ran these through our analyzer. It wasn't clear to me, were you saying you ran them through and it said, yes, they're safe? Or did it run them through and have problems and that was where you were getting your future work from?
No, Verasco was able to run program and say there is no false alarm in this program, they are safe.
Wow, okay, good.
Unfortunately, that's all the time we have for questions. Let's thank Sandrine again.